stereoisomers, but second part of stereoisomers is configurational stereoisomers. So conformational stereoisomers. In conformational stereoisomers, we have discussed about eclipse forms, target form. I told you that conformers can easily convert to target fluid, easily converted into each other by rotation about CC single group. Now, what's different between conformational and configurational stereoisomers? In configurational stereoisomers, first of all, you need carbon, which is bonded with 4 different substituents. For example, like this, if you have carbon, Cl, F, Br, and H, for example. In this molecule, you have carbon, which is bonded with 4 different substituents. It's important in optical isomers. So, these substituents can arrange in the space into waves, like this or like this. You see? So, their arrangement is different. So, they are stereoisomers of each other, and they are conformers of, configurational stereoisomers of each other. Now look, here is an example where you have the substituent Cl, Br, F, H. As you see, these 2 molecules are mirror imaging of each other. Yeah? So, quickly, configurational stereoisomers, which are mirror imaging of each other, are enantiomers. Enantiomers. Now, in this case, you have some letters instead substitutes. Once again, these 2 structures are enantiomers of each other. Why? Because of they are mirror imaging. And we have guys. Close the door. So once again, enantiomers are stereoisomers that which are optical. That's all. Take your place. And silence, please. So once again, in stereoisomers, where you have chiral carbon is carbon, which has 4 different substituents. We can discuss about optical isomers, and if 2 molecules are mirror imaging of each other, so they are enantiomers of each other, like this. So these 2 molecules are enantiomers of each other because they are mirror imaging of each other. So enantiomers have same physical properties, same chemical properties, but they have they have some differences in biological activity, and they have one physical property is optical activity. This one is their ability to rotate polarized light plane to the left side or to the right side. So enantiomers have the same absolute angle, absolute value of this rotation angle, but different direction. If one rotates to the left side, second one rotates to the right side. This is the difference between them. All other properties are the same, except some biological properties. Now, once again, if you have one chiral carbon in the molecule, or carbon which is bonded with 4 different substituents, we can discuss about enantiomers if they are mirror imaging of each other. Now look, as our 2 heads, they are mirror mirror image of each other. Our left hand in the mirror we can see as our right hand. Yeah, so they are mirror image of each other, so they are enantiomers of each other. Now look, if you have this molecule, you see, here you have molecule and you have 4 different substituents. This molecule and its mirror image are 2 different molecules, are 2 different compounds, but they are stereoisomers of each other, they are configurational isomers of each other, and their name is enantiomers. This is how they rotate this polarized light. You see, this is plane polarization, plane, and after passing this light in the solution which contains this optical active compound, which is once again has chiral carbon. So this polarized light rotates to the left side or to the right side. As you see, these 2 compounds are 2 enantiomers, and they rotate this polarized light to the left side or to the right side. But the angle is the same, as you see. Angle is same. Now, this is version if you have enantiomers. Now look, if you take a solution which contains equal amount of enantiomers, so 50-50. So in this case, you get mixture which is optically inactive. Why? Because of action of these 2 molecules neutralize each other's action. If one rotates to the left side, second one rotates to the right side. And because of absolute value of this angle is the same, so finally you get mixture which is optically inactive. Now the name of this solution is a racematic mixture. Once again, racematic mixture is a mixture which contains equimolar or equal amount of 2 enantiomers. And racematic mixture is not optically active. Now, once again, here is about their chemical properties. That chemical and physical properties are the same, but they rotate this polarized light right to the opposite directions. And second, their property is their reaction with other chiral molecules. So they can react with different mechanisms. That's why they have different biological activities, sometimes, but not always. Now look, how you can determine, you have here in this compound chiral carbon or stereogenic carbon or not. Has this molecule optical activity or not? Guys, have this molecule so optical activity or not. So as you see in this molecule, it's very easy. You see that you have 4 different substituents, so you can discuss about optical activity of this molecule. Now what about if you have only name of the compound? How you can understand this molecule is optically active or not, this compound, has this property or not? Now look, for example, if you have propan 2 also, in this case you have to know how to write structure from the name. Propan 2O, what it means? You have 3 carbonated, and in the middle you have OH group. Yeah? CH3, CH, OH, CH3. If you have this molecule, so here, this carbon is not chiral carbon because it has 3 same substituents. This carbon once again is not chiral carbon. Now what about this one? If I write a molecule like this, H. So, as you see, you have 2 same structures and 2 different. So, because of here you have 2 same groups, CH3 groups. So, this one is not chiral carbon and this molecule is not optically active molecule. Now what about 2-chlorobutane? Butane, you know, that contains 4 carbonated, 2-chloro. So here you have 1 Cl, H, CH2, CH3. Now let's discuss about this carbon because of other carbons have 2 or 3 H atoms. It means so that they are not chiral carbons. Now what about this one? 1 2, 3, and this is together 4. So here you have chiral carbon, so you have stereogenic center here, so this molecule has stereogenic center, and this one is optically active, and here we can discuss about enantiomers. So molecules which are mirror images of each other. Now, why it's very different? It's very important. Their structures, and you have R or S system of enantiomers. I explained this. First of all, now look. In 116, some drug is thalidomide. This was given to the pregnant women, and the results were very horrible results because of children, you see, without hands. Why? Because of here, look, you have two structures, two sterilizers, two enantiomers of this molecule. S enantiomer is effective drug, but R enantiomer is dangerous drug. And because of they give this drug, this version, second one, that's why here children have no hands, and they have difficult
shapes.
Yes. Now how you can determine which is absolute configuration of your molecule. What about determination of absolute configuration? First of all, remember please that which one rotates to the left side. We can sign this like minus, which rotates to the right side. It means plus. But this is only shows you their ability to which side polarized plane rotates. But this is not information about their absolute configuration. For determination absolute configuration of these molecules, you need Kahn-Prelog-Ingold's system. Now what it means? Here you have some steps. According to these steps, you can determine you have R absolute configuration or S absolute configuration. Now let's start and let's discuss about these systems. I write directly here. Now, which steps you need here? First of all, for example, if you have this molecule, C, Cl, F, Br, and H. This is three denomination of this molecule, yeah? So, you can write this molecule on the plane. So, these formulas we call Fisher's projections. In this point, you mean that you have chiral couple. So, in this point, is this couple. Now let's write other substituents. These two groups are in front of us, and this one on the left side, and this back. So now look, F, Cl, H, Br. This is one version. And second version is mirror imaging. It's mirror imaging. Looks like this, yeah? H, Cl, F, Br. Once again, these two molecules are two different molecules, and they correspond to two enantiomers because of their mirror imaging of each other. Now, how we can determine their absolute configuration? By Kahn-Ingold-Prelog system. It's the abbreviation of this system is SIP system, Kahn-Ingold-Prelog system, or RS configuration system. First of all, you need to determine which group has the highest priority, which one has the lowest priority. Now, how you can determine this? According to their atomic numbers. If you have monoatomic substituents like this, it's the simplest version. So F, Cl, H, Br. In the periodic table, you can find these elements and their atomic numbers. S atomic number is 9. Bromide's atomic number 55, 1 and 17. Which one has the lowest atomic number? This one is junior group. This one has the lowest priority, and this is number 4. So this age group is number 4. Then, which one has the highest atomic number? This one, yeah? So this is number 1, the highest priority group. This is number 1, this is number 3, and this one is number 2. Now look, after that, after determination, so which is junior group, which one is major group, please omit this group which has the lowest priority. And then look how your priority decreases. And remember that number 1 is group with the highest priority. This is major group. So you have anti-clockwise direction. Yeah. So this is absolute configuration of this one has to be S. Then look at your lowest group. If your lowest group on the horizontal line, so you have to change this as absolute configuration to up. So finally, in this case, you get that your molecule's absolute configuration is up. Now once again here, this is number 1, this is number 2, number 3, and number 4. Once again, omit your junior group. And look how your priority decreases. In this case, clockwise, yeah? If your priority decreases clockwise, so you have R configuration. After that, look on your junior group. In this group, on the horizontal line. So once again, you have to change configuration R to S. And finally, your absolute configuration S. As you see, if you have enantiomers. So if one has R configuration, second one always has S configuration. If first one S configuration, second one always has R configuration. Now, if you have more complex substituent groups here, how you can determine, in this case, your absolute configuration? Now, if you have this version, CH3, H, Cl, and CH2, CH3. So, first of all, right, which substituents you have here? Here you have CH3, then CH2, CH3, H, and Cl. In this case, what is understand their numbers because of H has number 1 atomic number, so it has to be number 4, and Cl has to be number 1. Now what about these two structures? Because of Cl's atomic number 17. H atom's atomic number 1. That's why this is number 1, this is number 4. Now why are not these two groups number 1? Because of here, always look at the first atom. First atom in group which is bonded with chiral carbon. Here, your first group is carbon. Yeah? Here, your first group is once again carbon. So, carbon and carbon, both of them have the same atomic number. So here, you can't understand, according to first atom, their priority. After that, look at the next atoms. So, for this carbon, I write like this, look, H, H, H. Now what about here? C, H, H, and then goes carbon, yeah? Here, you have to find first difference between them. between this substituents. So here you have H, here you have carbon. Which one is number? Two.
Number 2 is CH2.
Yes, this one is number 2 and this one is number 3. Now let's write here this priorities. 1, 4, 2, and 3. After that, don't look at this, omit this H atom, and determine how your priority decreases.
CL is 1, not 4.
No, here I write 1. Now look, your priority decreases clockwise. So it has to be up. After that, look at your lowest group. Yes. Because of this one on the horizontal line, so once again you have to change R to S, and your final absolute configuration is S.
So it will be S, not R.
Clockwise means that you have R. If your priority decreases clockwise, so you have R configuration. If your priority decreases anti-clockwise, so you have S configuration. So you have S configuration, and after that, look at your junior group. If your junior group on the horizontal line, only in this case you have to change configuration, R to S or S to 1. Now, only in this case. Now let's discuss about another measure, another example. Yeah. So, if you have this molecule, look. So, we have substituents. CH2, CH3. Second one is C double bond OH. Sorry.
This is outline.
You are not listening. Silence, please. C double bond OH and C double bond OCH3. Now, let's start. In all cases, you have carbon atom, so you have to look at the next atoms and find the first difference which you have in this molecule.
The next one.
Now, in first one, you have look C, H, and C. So H, C. In second one, now look, if you see double bond or if you see triple bond, duplicate or triplicate this atom. Because of here you have double bond with oxygen, so you have to duplicate this O. So here have to be O, and H. Now what about this one? O, and O. 3 O atoms. Because of with oxygen, once again you have double bond. So O, and O. Now what about this one?
H?
O. So you need first next atoms. So next atom for this carbon is oxygen, not H.
Yes.
Now what about this one? O, and C. Now let's discuss. These two groups are the same. So here you have difference, yeah? H atoms atomic number 1, oxygen's atomic number 8, and carbon's atomic number 6. So in this case, which one has the highest priority?
No, second.
Third one. If you start from here, third one. This one is number 1. This is number 2, and this is number 3.
Can
Now
you
let's
explain
try.
again, please?
Once again, if you see double bond with any atom, so if your carbon has double bond with oxygen or with nitrogen triple bond, so you have to duplicate these two atoms if you have double bond, and triplicate this element atom if you have triple bond. Here carbon has double bond with oxygen.
Yes.
So duplicate O, and then this atom.
Hydrogen.
Now here goes oxygen with this carbon.
We don't
That's why I write here 3 oxygen atoms. Here, O, and carbon.
Yes.
So, here you have difference between atoms. First difference you have here, yeah? Because of carbon's atomic number is 6, oxygen's atomic number 8, and H's atomic
It's
number...
8 or 6 oxygen?
Oh, 8. 8.
Atomic number.
Number of valence electrons is 6, but atomic number is 8.
Yes.
That's why this one is number 1, this is number 2, this is number 3. Now let's write here. This is number 4, the junior group. This is number 1, number 2, number 3, and number 4. Don't look, oh sorry, I mixed something. Number 2. Yes. Now don't look at number 4. And first of all, determine your priority. 1, 2, 3. On.
R to S.
No.
R.
Because of your lowest group on the vertical line. So in this case, you will not change your absolute configuration. So R stays
Please, can you repeat?
once again. If your lowest group on the horizontal line, vertical line, in this case, this one is your lowest group. If your lowest group on the vertical line, so you wouldn't change your absolute configuration. So R stays as R.
What about if it's S?
S stays as S. That's all.
For example, in this case, number 2 in the right side, number 3 in the left side.
Okay, now let's discuss about this.
For example, don't clean it, just change the number. 2 and 3.
Okay, I write here. What was here? CH2, yeah? And here was C double bond, OH. So this is number 4. And
This is number 3.
Number
3. 3.
3.
It will be R for S. R.
Just first of all, let's look how this priority decreases. Yeah? 1, 2, 3.
R to S.
It has to be R, but because of your lowest group on the horizontal line, so you have to change R to S, and finally you have S absolute configuration. You understand? So, first step is determination priorities. Next step is determination configuration. After that, look at the lowest group. If this one on the horizontal line, so you have to change. If your lowest group on the vertical line, so
You don't have to
you
change.
don't have to change. You have the same absolute configuration.
Got it.
Okay. Now, what about? This is about this. What about compounds? What about compounds in which you have 2 chiral carbons? Not 1, but 2 chiral carbons, or 3 chiral carbons. How many stereoisomers you have here? So how many configuration of stereoisomers you have here? You can calculate this one by the formula 2 nth degree, where n is number of chiral carbons. So, for example, if you have 2 chiral carbons, so stereoisomers number will be 4. If you have 3 chiral carbons, so it have to be 8. If you have 4 chiral carbons, so you have 16 stereoisomers. Now let's discuss about this molecule. COOH, CHOH, CHOH, COOH. Tell me please, how many chiral carbons do you have here? 2. Second and third. This one is tartaric acid. this acid you have in orange juice and in many fruits. This tartaric acid. So this is your chiral carbon and this one your chiral carbon. So if you have two chiral carbons, so this one has 4 isomers. Now look, first of all, let's write Fisher's projections for this molecule. Like this. Here you need 2 lines. Why? Because of here you have 2 chiral carbons. This is one version. Second one, if I want to draw enantiomer of this one, so I have to write its mirror image. Yeah? So, OH, H, OH, H, COOH, and COOH. Now tell me please, these 2 structures are enantiomers or not?
Not.
Sorry. I need enantiomers.
Yes.
They are enantiomers of each other, yeah? Why? Because of their mirror imaging of each other. So they have same physical, same chemical properties except optical activity. Now what about this structure? What about this structure? This structure isn't mirror imaging of this one or mirror imaging of this one.
Yes.
So if they are not mirror imaging of each other,
So, yes.
they are diastereomers. These 2 structures are enantiomers and these 2 structures are diastereomers. So if I want to draw the enantiomer for this one, I have to write like this. H, O, H, O, H. Oh, sorry. O, I, O, H. And here I have to write H, C, O, H. Now these 2 structures, as you see, you have here 4 stereoisomers.
This is
yeah?
mirror.
4 structures. These 2 are enantiomers of each other. These 2 molecules are enantiomers of each other. But these and these, this one and this one, this one and this one, and this one are diastereomers of each other.
Can you please just write the name if they are mirror imaging?
So, if 2 molecules are mirror imaging of each other, like our one has, they are enantiomers.
Can you write the name?
Enantiomers. If they are not mirror imaging of each other, so they are diastereomers. So, these and these are diastereomers of each other. These 2 structures are enantiomers of each other. Now look, diastereomers have different physical properties, different chemical properties, and different biological properties too. Now let's discuss about this molecule. Of course, these 2 structures and these 2 structures are optical active structures. Now what about this one? In this molecule, you can pass through this molecule symmetry of plane symmetry. Now look, this part is mirror imaging of this part. If you put together, so you get the same. Yeah? Now look, if you can pass through the molecule plane of symmetry, so this molecule is optically inactive. Optically inactive. Now why? And the name of this one is mesophore. Mesophore, once again, is optically inactive because of one part of molecule is mirror imaging of other parts molecule. Now let's discuss about this, why this one is optically inactive molecule. Look. In this case, don't look at this part. Let's discuss about three substituents. This is number 4. This one has the lowest priority. This is number 1 because of oxygen's atomic number is 8. And this is number 2. So 1, 2. Your priority goes anticlockwise. So these carbons, absolute configuration had to be S. But because of your lowest group on the horizontal line, so you have to change. And finally you have R. This is first carbon, this is second, third, and fourth carbon. So you have 2 R. Second carbon's absolute configuration is R. Now what about this? This is number 1, this is number 2, and this is number once again 4. 1, 2. So you have clockwise, it has to be R, but then you change, and finally you have 3S. Now look, if one part of this molecule rotates polarized light to the left side, second one rotates to the right side. Finally, you have optically inactive compound, or mesophore of this compound. Like in racematic mixture, but in racematic mixture you have 2 compounds, 2 enantiomers together. Equimolar amount of 2 enantiomers. In this molecule, directly in the molecule, you have mirror imaging of 2 parts. That's why this molecule is optically inactive. And the name of this one is mesophore. Mesophore. But in any case, this one is diastereomer of this molecule. This mesophore is once again, optically, this mesophore optically inactive because of action of one carbon. 2 R because of second carbon's absolute configuration is R. This is 1 carbon, second carbon, third, and fourth carbon. So second carbon, this is number 1, this is number 2. Anticlockwise, yeah? Because of your lowest group on the horizontal line, finally you change your absolute configuration, and second carbon's absolute configuration is R. Third carbon.
Why don't change R to S?
Because of your lowest group.
Yes, why don't change R to S?
I have changed.
Okay.
So you have S, and after that I change, you get R. Now, once again, this molecule is not optically active because of here in the molecule you can one part of the molecule is mirror. Guys, you two, go out. You two, go out. Quickly, go out. Out. You two, out. Quickly, you and you. Go out. Quickly.
This is only 8 minutes we
You
have.
guys my time. Quickly. So, we will do this, but okay, write like this. Without this part. In this case, you need number 1 and number 2. That's just.
We don't have number 4 because only 3 atoms here.
Yes. No, this you can discuss, but in this moment you don't need force substitute. You need number 1 and number 2. Now look, if you have alkene, as you remember, we discussed about cis-trans isomers in alkenes, where you have double bond and you have at least one same group with the carbons which are in the double bonds.
Yes.
Now, this is one type of, once again, stereoisomers. it's geometric stereoisomers. Geometric stereoisomers where you have cis isomer if your same groups are on the one side of your double bond plane, and you have trans if these same groups are like this on the opposite sides. Now, if you have this version, CH3, C, H, double bond, C, Cl, CH3. Now let's open this, let's write separately all substitutes which of carbons which are in the double bond. So C, double bond, 6, H, CH3, and Cl, CH3. As you see here, you have one pair of same groups, it's CH3. If these two same groups are on the one plane of your double bond, on the one side of your double bond plane, so you have cis isomers. If they are on the opposite sides, you have trans. Now, where is what?
CL, this is CL.
Now, what about this model? What about this model? Here, as you see, you once again you have your HCl, it's the same. I don't like this example.
We do.
I don't like to.
So, this is trans. You can discuss here about geometric isomers. Now, if you have this version, CH2, CH3. In this case, you have that same groups. You have that same groups with carbons which are in the double bond. So here you can't discuss about geometric isomers or cis-trans isomers. Now let's discuss about other type of stereoisomers. It's EZ isomer. EZ. Once again, let's write separately these constituents H here and Cl here. This carbon has CH3 and H as substituents, and this carbon Cl and CH2 CH3. Now separate. If groups which with the highest priority are on the one side of your double bond plane, so you have Z isomer. If on the opposite side, so you have E stereoisomer. So this one.
CL, C2,
H, CH3. This is group with highest priority, H, and this one with low priority. Separate this molecule and discuss about two substituents with one carbon and with second carbon. Now with second carbon, this is number 17. So this has higher priority than this group. Look here, your same priority groups are on the opposite sides. So that's why this one is E. E.
Where is it?
High, low, low. You see?
like the trans.
This is E. And next one is... Wait. No, I still this one. Now I draw another version. High, low, high, low. So in this case, your same priority groups are on the one side of your double bond plane. So in this case, you have Z. It's from German words. E means entgegen, so it's separate. And Z means to summer all together.
Iron.
H. Now, group number 4. You have to be here. Group